Hi, this is Dr. Liu. We have a metal hoop with mass and radius. It rolled without slipping on the horizontal floor. Then a ramp is placed on the floor. The hoop rolls up the incline without slipping to a vertical height of 0.4 meters before stopping. The ramp has a length of 2.0 meters along the incline. The question is to find the speed of the hoop before it reached the ramp. So let's do a diagram. So we have, oh, that's okay, tilted. Okay, this is better. We have incline. We also have a hoop that rolls forward. So we have a height of 0.4 meters. So this is 0.4. And the length 2.0. So the hoop rolls and it kind of stops here. So let's just draw the center of the hoop here as it stops. Okay. And we can use energy conservation, including rotational kinetic energy. So here, this is a timestamp of 1, of 2. So 1 has rotational kinetic energy. It also has translational kinetic energy. 2 has just gravitational potential energy. There's no kinetic energy. So let's write down mechanical energy, which is kinetic energy. Let's just use KE, kinetic energy, plus PE, potential energy. In our case, it has this translational kinetic energy of the center and 1/2 I omega squared. This is rotational kinetic energy around the center, and then mgy. Alright, so 3 terms. And rolling without slipping, what this means is the rotation and translation are related. It means velocity linear is velocity angular times radius r. So we can replace this angular velocity with this expression. So angular velocity is velocity over r, right? Because we were asked the speed of hoop before it reached the ramp, not the angular speed. Okay. So our mechanical energy now becomes 1/2 mv squared plus 1/2 I v over r parentheses squared plus mgy. And this I is I of a hoop or ring, right? I ring, and that's here, mr squared. So this is mr squared, and I can plug it into the energy term. So I have 1/2 mv squared plus 1/2 mr squared, and then the square of this is v squared over r squared. And we can divide this out, and this is another mr squared. Interesting. Well, if you have a ring or a hoop, you have just as much translational kinetic energy as rotational. So this is translational. This is rotational. Right? If you just assume something is sliding, then it's not rotating, then this term is entirely missing. We've been doing that for a while, until the recent chapter about rotation. So this is accounting for the fact that something is rolling forward. It's not only moving forward, it's also rotating around its center. So we have 1/2 and 1/2 the whole mv squared. It looks a little weird compared to what we had before, but this is actually a bit more realistic. So now you have this as the total energy. So we can write down how much energy here, how much energy here, and just equate them. All right, we have plenty of space. Let's just move to the right. So E1, we're here, and just mv squared. there's no height, so okay, well, there's no height because we should be doing this, setting up an axis with the origin at that ground level. So that's just that. I can put a 1 there, indicating the velocity at that point in time. And then E2 is, well, we roll, and stop. So there's no kinetic energy. It's just the gravitational potential energy. And this is a known quantity. So let's set E1 equal to E2. So we have mv1 squared equals mgy2. And we can divide out the mass. The mass doesn't matter. So v1 is equal to gy2 square root. So that is 9.8 times 0.4. So this is roughly a 4. 0.4 times 10 is 4, right? So let's just do an approximate. So roughly a square root of 4, so roughly a 2 meters per second. I think I'm off by about a 1%, so it's probably 1.99. Since the numbers are different for different students, I don't think I should be very careful with this number exactly. I'm just showing you how the process is done. So back here, the kinetic energy now includes two terms: translation through the of the center of mass, the entire thing moving, and there's a rotation around that center. So this additional term, with this rolling without slipping condition, it turns into this. And then with the exact shape of the object, you may not be getting the hoop, you may be getting a ring, or maybe, sorry, not ring, the same. Maybe getting a disc, maybe you're getting a sphere, solid sphere, maybe a hollow shell. They're all different by this quantity here. What is the rotational inertia? How many mr squared? Right. So if you had a disk, it would be half mr squared. So this will differ here, and whatever you plug into the I will depend on the shape. So the sum may not be the half and half, maybe a half and a quarter if you had a disk. And then the total rotational kinetic energy and translated kinetic energy is no longer going to be just mv squared. It depends on the shape, but this is all the same, right? And then you have a slightly different value here, a different factor that's still equal to this, and then you can solve for v1. Thank you.